Welcome everyone. So in our last session, we had just started building the logistic regression. Let me just quickly recap what all we did. In performing the logistic regression, first step is basically, this is what I explained, that logistic regression is all about log odds, and using log odds, we are trying to build a linear equation with respect to the log odds. First step, we created our data set for building the model. After having created the data set for building the model, we first do exploratory data analysis. We try to understand the data. So we executed summary, quantile, some of these basic functions. We have to do some outlier treatment. So we try to find outliers and do capping, flooring. We have to do missing value imputation. So those are the things which we did. Missing value imputation can be done mean value imputation, or you can build a linear equation for the missing values and then impute using the linear equation, or you can do imputation using k nearest neighbor and so forth. And then I inform that to identify variables which are significant, we have a concept called information value. We saw information value, and in the last session we did extensive amount of visualization, pattern detection. We saw how trends can be modified and how those trends can make sense. Yeah. And at times, sometimes based upon the trends, we may have to do variable transformation. And then we moved into model development stage. This is where we were there. When we do model development, we already have this data, LRDF, and then we split it in development, validation, or we can split it in dev, well, and holdout, and so forth. And on the development, we start building the model. To build the model, the step is very simple. We have to use a GLM function. We specify target. We want to build a target as a function of variables. So all the variables with respect to which we are trying to build the model has to come here. These variables are in which data set? We have to specify the name, and family is binomial because our target is dichotomous. And when we run summary, we get a summary output. So let me quickly run this step in R. Okay. So let us quickly create our data set. I have already shared you this lrdf.r data. Parallelly, you can quickly run the codes with me. So you have to run this part of the code. Set the working directory where LRDF is set, and then load the file. By loading it, you will have this data available. Quickly, let me show this view. Just for your remembering, this is our target. These are our various predictor variables against which we are building the model. All these steps we have to skip because these were import and creating the data set. Merging, import, merging, we don't have to do. Summary I'm not running now. Summary and all those things. Some things which is basically outlier treatment. I'll just quickly do outlier treatment. Okay, this part of the code has to be done. Missing value, I don't need the decile function. Holding period imputed, sorry. Holding period imputed. Okay, this is what we have required. Occupation, we have to cast it as a, and then we have imputed the missing to missing. Okay, all these steps we had done. Yeah, so this is what our summary data is, and now here I'm just copying this. Quickly let me run summary to show that. These are the three variables we have done capping for outlier treatment, holding period imputation, and occupation imputed is what we have done. Okay, so here we did sampling. So I'm doing random number generation. Okay, my data, I have to run this step, my data, random number generation, and then I have split it into three sample: development, validation, holdout. These are the three data sets that we are creating. Okay, let us quickly check the numbers. It will be in 50-30-20 proportion. So my data is 20,000, 10,000, 6,000 and 4,000. That's the approximate proportion that we are getting. Okay. Target rate in each of these data set 4.3, 4.4, 4.5. Okay. So okay. So I'll just build the model. This is the step we executed last time. Because occupation imputed is variable is there, I'm not taking occupation variable. HP imputed variable is there, so I'm not taking the original holding period. Last time we saw gender was not coming significant, so we dropped gender variable. Yeah, and this is where we had left. When I run summary, this is where we left. If I had asked the question, this is 2.284, and if I do plus or minus, then this value was changing sign, right? I had asked what should we be doing when this is the scenario. Okay, let's understand what can be done. If a particular variable changes its sign, how do we manage it? Okay, this is my code. So here, let me copy this again to Excel. Data text to columns and delimited based upon space. Finish. Change this home formatting. I'll change it. Okay. Okay, some of them is moved. I'm not bothered of it, but yeah. So here, what is the solution you people found if a particular variable changes its sign? What is the solution? None of you tried? Okay. Let us see why last time when we executed self-employed, now in this scenario it is not changing, but last time it changed its sign. So what will be the solution? If I do plus, this is the beta, and if I do minus, this is the beta. If there is a change in sign, you can go to your basics and see what is the probability of various cases. So to get that, what I'll do is I'll do table LR underscore DF dollar target with respect to occupation dollar imputed. Let us take this cross tab. This is the cross tab I get. Beta text to column delimited, next, finish. So this is my target, total equal to sum. What is the response rate? is equal to 208 divided by this number. The sign change was for professional. Let me see what is the professional category. Minus 0.64 and 0.15 minus this. Okay, so in this case it's not there. Now if this something of this kind happens, what you should be doing is the response rate of missing and professional very close to each other? What you should do is combine those categories. If there is a particular variable, the beta is not coming stable. Now in this case there is no sign change. At least here, let me do plus or minus for all of these variables. We did one standard error. It's both negative, all negatives. So there is no sign change. So I can go ahead and use it. But it is quite possible in validation, if we run this thing on validation, it will show that the beta is not stable. In that case, what we have to do is, because the response rate of this and this category is not very far off from each other, you can take a judgmental call and say, I am going to club these two categories as one category. What it means is, what this means is, you have a new variable saying LRDF dollar derived variable on occupation is equal to if else LRDF dollar occupation imputed equal to, what is the value? Missing. It's capital. So let me put it to missing, or this category which was matching is prof. If either of these is matching, then I'll say it, I'll create a new category. Else I'll continue with the old occupation only. Okay. So new variable creation. dv is actually a derived variable. Let us see how does the numbers look. Oh, there's something problem. We wrote a wrong syntax. Let me. Okay. So this is how this syntax should have been. Instead of double pipe, I should have used single pipe. So this is what it is. Okay. So here the two categories, which is professional and missing, are now combined. How many observations were there? Zeros 9691 9691, and this one is 2028 and 2429 429. Yeah, so this is what we have done. Now the change in sign will not happen, because when there was a change in sign earlier, last time when we executed, the beta of missing was 0, and we saw the beta of this professional was changing sign from negative and overlapping with 0. That overlap indicates that variable should be, that category should actually merge with the category on which it is overlapping. Okay, so here that's what we have done. Once you have done it, again you have to take your code, you have to come here. This is the iteration that you have to keep doing. Each variable, if the betas are not stable, you have to keep making it stable. So now what is the new variable that we have created? dv underscore occupation. Okay, so with this, oh, I actually changed it LRDF dv occupation, but I'm building the model on mydata.dev. Because I'm building it on mydata.dev, I need to again create these dev val holdout. Either I again create it. See, again is a chance thing that I actually changed the variable and created it in the original thing, but I should not be doing it, because now I'm in a development process. I'm not in a validation process. So again, these numbers which I got in the table, this cross tab should be with dev sample, because when you are working with a development sample, now all statistics you have to constantly derive based on dev sample, not on the original sample. So this is my mistake. So here also this will become okay. I've run it. Let me run this thing once again. No, there's something wrong. Okay, that is right. My data.dev. Okay, sorry. This should be with respect to this column. Yeah, prof missing. Yeah. So as you work, you have to keep constantly doing this cross check. Yeah, I did a table with respect to original column, and I'm now doing a rechecking whether the variable has become corrected, merging of the categories has happened, but I'm still doing it with the original column. That don't make sense. Okay, now you have done that. So my data.dev, this data set, we have to rebuild the logistic regression. And believe me, these practical back and forth will keep happening when you are building the model. You may sometimes make it change in the original data set, but you are building the model on a development sample. You have to remember that you have to make it changes on the development samples. So let me run this. I build the model. After building the model, I again have to see the summary of this model. Now see, all categories are stable. All categories are stable. Earlier, some categories in occupation were not stable and there was no 3-star rating. Still, I've got one here element, but I can skip it. I can, to some extent, I can ignore it. Once you are done, again, what is the step you have to do? Take this. Check whether there is a sign change. Take data text to columns. Okay. This, there's some amount of this thing moving back and forth. I'll ignore that. I'll focus on the 2 columns. Intercept, I'm not bothered. But for these variables, I have to see whether there is a sign change. Plus standard error minus standard error. Let us do formatting also. Minus 3.73 e raised to 0.6 and this is e raised to minus 7, so that not a much issue. Okay. And number of create transaction. Oh, sorry. This plus this minus this. Yeah. Negative, negative, no change. Positive, positive, no sign change. Positive, positive, no sign change. Negative, negative, no sign change. Negative, negative, no sign change. Positive, positive, no sign change. Negative, negative, no sign change. Okay. So all my betas are very stable. Why is balance beta coming to be too small? Minus 0.0003736 something. Why is the balance beta coming such small value? Because the balance variable is in lakhs. Are you getting? Because the balance variable is in lakhs. That's why when the numbers which are in lakhs, if you recollect, balance variable outlier was 12 lakh something. P99 was around 7 lakhs. Right? So if you don't want this beta to come too small, what is the alternative you can do? What option you have? We have capped it. We have capped it. But I can still do scale transformation. I'll say lakh is equal to 100. Lakh is equivalent to 100. Any balance which is there, I'll say I'll divide it by 1000. I can do scale transformation. Values will come down. In that case, beta will go up. See, if you're not happy with this small beta, because see all other betas, if you see all other betas, after at decimal or at second position. For all of these betas, there is something number, but here after 4 decimal also, this number is like 0 only. If you are not happy with that kind of thing, then simple solution is we are working with mydata.dev dollar dv valcap. Okay, so I'm now doing it equal to mydata.dev dollar valcap divided by say 1000. So I'm changing all values and scaling it down, building down by a ratio of 1000. And now you can take this variable and build the model. For example, let me take this variable now. See, now the beta is much more, you're able to see it very clearly. Okay, so that is on.
So like more we can reduce it by 100 as well.
You could have reduced it by 10,000 also. You can reconvert it also. If you are very comfortable saying that, see, it's up to you whether you are comfortable, not comfortable. If you are very comfortable, because in that case, what will happen when at implementation, you have to remember that you have to do this. You have to do that. See, any transformation you do, I'm okay. I say, okay, with me, this balance, I'm okay. Yeah. Because it's just e raised to minus 0.6. Now it is coming e raised to minus 0.3. So it's just matter of that. So I'm comfortable. I'll go with that. So this is part of your model development stage. So when now here, if you recollect, if you see, I'm working with just 8 variables. Working with 8 variables itself is showing me that I have to do these iterations back and forth. When we work, actually we'll have 200 variables. We'll have 250 variables. We'll have 300 variables. Definitely using information value, you're going to scale down 250 variables to 50 variables. Because many of them which are less significant based on IV, you will say, okay, they are not important. You will remove them. But still 50 variables is a good number of variables with which you have to keep playing. You cannot, even when you run an iteration, in a given iteration, if 10 variables comes insignificant, you cannot drop 10 variables in one go. You may drop them iteratively, 1 or 2 at a time. Okay? Checking the value IV values. No, you can see, typically we don't drop all of them in one go. What happens is, if there are 10 variables which are coming insignificant, because of multicollinearity also, sometimes there's 2 variables which are significant, one of them may go off. Because of the multicollinearity phenomena also, important variables may become not important. Yeah, so those challenges are there. That's the reason why you keep doing these iterations, and parallelly you have to check multicollinearity. Now if there are many variables, you think that variable should have been significant. IV shows that variable is significant, but when you are running the iteration, logistic regression with many variables in one go, so it's a multinomial logistic regression, because there are many predictor variables. When you're running it, a significant variable is not coming significant. The way to check out is variance inflation factor. So what I'll do is, I can parallelly quickly check variance inflation factor. This is my model. In linear regression, we already saw that using a char package, we can do variance inflation factor. If VIF is above 5, what do we do? If VIF is above 5, which means there is a collinearity. Two or more variables are collinear. So, no, that is IV. If VIF, variance inflation factor, in my case, in this case, all the generalized VIFs, are around 1, which means the variables balance cap, number of credit transactions, score, holding period imputed, and derived variable of occupation, they are not collinear with each other. So I don't have a multicollinearity phenomena in this data set. So I can go ahead and safely assume now this model, at least from a development point of view, this model is stable. So when I check the VIF in this presentation, because I executed with only 3 variables, it's showing with 3 variables. We did not try age bucket, or was age not coming significant? Let me quickly do with age also. Here I have not tried with age. Plus age plus age underscore BKT. I think so we tried it last time, but let me quickly run it again. Control R, summary. Okay. Okay. Age. If you see, there is no star. Age is now saying that age variable is insignificant. Yeah. Age variable indicates that age is insignificant. If you recollect the age trend was something like this. This was the trend. 40, 41, 42, 43, around that. This was the trend. And then I said that we have to do mirroring with respect to say 43. And then I can bring those variables here. So, and make it stable. So let us try doing that element. Okay. So let us do with respect to 43. I know the numbers. Is that code already written? No, that code is not there. So let us create that. Okay, so let us change our age variable. We are working on the dev data. So my data dot dev dollar dv. I have this convention. Once I enter into the modeling, to avoid any confusion with my original variables, I now keep doing dv underscore. dv because that helps me under a derived variable. This I derived it because when you're starting doing modeling, you'll never come to know what you derived, and because if you keep creating many variables, see these transformation, this is now transformation step. If you can transformation, model development, visualization, these 3 keep happening parallelly when you're building a model. So now I am in a derived variable, which is the transformation. So I'll now do a derived variable of age. Okay. And I know the logic that after 43, I have to make it a mirror image. So this equation will be if else age my data dot dev $age greater than 43. If it is greater than 43, then it should be my data dot dev $age minus my data dot dev age minus 43. So this part will give me how much it is more than 43, and that much I'm going to remove it from my data dot age. So I'm now going to create a mirror of that element. If it is less than 43, I'll do my data dot dev $age. I'm going to keep it as it is. And this is my new derived variable, which I'm now creating in the modeling ways. Because age did not come significant, I'll now drop this age and replace it by dev age. Okay, I'm assuming the variable would have been created properly, and I'm now going to run this my logit summary. Let us see. $age is coming as point. No, it's not coming significant. It is come as 0.20 p-value. The p-value has improvised. If you recollect, age p-value was 0.7175. But now it has, at least the p-value has come down from 0.775 to 0.2082, but it is still not significant. Because it is still not significant despite us doing the transformation. Despite us doing the transformation, it is still not significant. So what we can say is, okay, probably this variable is not significant given that there are other variables which are coming significant. Now after doing those attempts, I can decide to drop the variable. Yeah. And age buckets anyways are not coming significant. My age bucket variables also not coming significant. So because these variables are not coming significant, I'll say I'll drop age and age bucket both. Once I have decided, at a later iteration, it's quite possible you may again choose to bring that variable and again run a try. Again, please understand, you are working with 200, 300 variables, you have dropped it. At a later stage, you may still feel, hey, no, that variable should have come significant. And you may also again try. This is an iterative process. But here, I'm not going to stretch it more. I'm going to say that is not significant. I'm dropping that variable, and then I'll do a summary. And we have already seen with VIF, my logit, all my variables are stable. Is this model stable? How do you ensure that this model which you have built on a validation development sample and the betas that you have got are really going to hold in unknown, unseen data? To make that doubly sure, what you have to do is you have to run this logic on a validation sample also. You have to now run it on a validation sample, the regression process. After running the regression process on validation sample, you will get the betas. So what we will do is, what are the variables that we have now? We have balance cap, which is the original variable, number of credit transactions, which is actual variable, score, HP imputed, DV occupation. DV occupation is something that we created as a new derived variable. So I need to get that logic of DV occupation. This is the logic of DV occupation. I'll copy this. I take it. I have to change it on the val sample now. Okay. I have to create this variable on the, sorry, val val val. Okay. I have all the variables which are there in the val sample. I have to build the model on the validation sample. So I'll take that, my logit, I'll call it my logit underscore v. I'm giving it a new name to this model because it's a logistic on the validation sample, and the data set will be, well, I kept creating new variables, but I have not changed the C1 to 14. Minus C1 to, oh, minus C1 and 14. Those are the two variables which I'm dropping. Why was 14 dropped? Random number. No, see, 14 is random number. Just let us view it. View my logit. No, no, that is a random number. We are dropping the first column because it's a customer ID, and the 14th is this is factor 8. This 14 is basically a random number. So that's the reason why we had put that minus 14 also. To do the splitting, development, validation, holdout. Okay. So I've run this on the validation sample. Again, I have to see the summary on the validation sample of the model. First step, again, we have to see all the variables are stable or not. So the same set of variables are passed. All my variables are coming stable. Okay, I've checked that. If all variables are stable, I'll copy this. And let's paste it here. What got copied? Oh, it got copied from beginning. This is what I require. Copy. Okay. Data text to columns. Delimited. Space. Finish. Now what you have to do? This is your, what I'm doing is I'm just dropping all of these columns. Okay. Or hiding. Instead of dropping, I'll hide them. Let me take these two columns up parallel so I can better explain it. The reason I have taken all the columns is to ensure that the sequence is same. It may sometimes happen the sequence may change, right? So if there is some change in sequence, if you don't take the column names along with it, you may not know where the sequence is changing. Now what you have to do is, let me change this also to, I'll change the formatting to make it number. Okay. This is another test that we do. You typically do a ratio. Okay, you typically do a ratio. If the ratio between the dev variable beta estimates and the validation variable beta estimate, if that comes closer to 1, which means the beta estimate is very much closer to what it is. See, if there is a standard error which is too high, which means the beta estimate may not be the same consistently in dev and validation. So if the ratio is between very close to 1, you can say that the variables are stable. Typically this range permissible is 0.5 to 2. It's a permissible range. The reason why 0.5, if I'm doing this divided by this, it may come 0.5 also. If I'm doing the reverse, it may come 2. So basically if I do the ratio, in this case what I did is C4 divided by P4. Let me do the reverse. P4 divided by C4. So it will be 1.1. And here this is 0.5, so it is 1.8. So this shows that for self-employed non-professional there is a huge variance in the beta variable. For all others there is a very high amount of stability because they are very close to 1. And I'm going to ignore this because in categorical variable it is quite possible one of the categories may show a good amount of variance with respect to other categories, because categorical variables beta is influenced by the beta which is given to the other categories also. It is not just a standalone beta. Yeah. So I'm going to tolerate this 1.8 because all others, this is coming 1.01, this is coming 0.83 of the 4 categories. What are the 4 categories? Salaried, self-employed, non-professional, SENP. Which is the 4th category? Missing and professional, because we clubbed them. Now that missing and professional is not coming. If missing and professional is not coming, what is the beta of that? 0. Missing category beta is 0 because that is the baseline. That is a reference. When there is a categorical variable, one of them becomes the reference baseline. So that will become 0. So here I see the validation also it is holding. So this is how we validate the betas. There are 2 ways of validating. First we are going to do plus or minus. Second we are going to do on the validation sample. Typically this element we do at the fag end after we have completed the development on the model. After we have done the full model development and when we have seen the performance of the model on the development sample, then we do this validation, because we were just at the beta variable check. That's why I thought I'll show you on the validation sample also. Okay, typically that is done once you have completed the entire model on the dev sample. So after having built the model, I first see multicollinearity in this output, and in our output also we see all values are close to 1. Multicollinearity problem is not there. If the value is great, any value is greater than 5, definitely multicollinearity problem is there. So we have checked multicollinearity. Once I have checked multicollinearity, I need to see how good is my model. There are various model performance measures. One of the most important model performance measure is rank ordering. Okay. We'll now see what is rank ordering. Before that, what is the logistic regression model supposed to give? The logistic regression model is supposed to give probabilities. And in my second session, I explained how this probability is coming into play. Because though target variables are 1 and 0, I showed you when you aggregate data, say by age, in a given age bucket, there are certain customers who are responding and there are certain not responding. And when you do a ratio, you get the probability what percentage of customers are responding in that age bucket. And then we also saw that one dimension is not the right way of seeing. We have to see things in an n dimension. And that's where we move to logistic. So now logistic is going to give you probability for each and every customer. But if logistic is going to give you a probability for each and every customer, how do you estimate that probability? Yeah. So let us see that how do you estimate? Estimate is predict. How do you predict that probability? So let us see that. To compute the probability, you have a simple function called predict. Okay. My development model is stored in MyLogit. I need to change it to dev sample. What does predict function do? Predict function scores the given data, computes the probability for the given data. So here the model is in MyLogit. Which data I want to score? The development data. If you see this data, let us quickly see so that you people don't forget. There is no probability column as of now. dv age is the last column. Okay. Now I'll run this predict function. What does predict function do? It's a generic function which can be used for any type of model you build. The help is here. Predict is a generic function for predictions from the result of various model fitting functions. If you build a classification tree technique, which we are going to see in the upcoming session, if you build random forest, which we are going to learn, so it's a generic function. Any model you have, you pass that model. The entire equation of the model is in the model object. In this case, MyLogit. Entire equation is in the model object. In this case, MyLogit. And what is the equation? Equation is y is equal to alpha plus beta 1 x1 plus beta 2 x2. And if you see this, this is alpha, this is beta 1, this is beta 2, this is beta 3, beta 4, beta 5. All the betas are there. The equation is there. Because that, when I do summary MyLogit, only then I get these, no? Which means the equation is with that object. If the equation is with that object, it can be used to score. So I'll use this, and type equal to response. I'm saying by type equal to response, I'm saying I want probabilities. Yeah. So when I run this, you see probabilities have come up.
So this is like close to 1 or something.
No, this will not be close to 1. This will be the probability of this customer responding is what? Okay. So let me show you it in head, using head command. So what is the probability of a customer responding? So we can estimate these probabilities also. How we can estimate? Let us do that. I'll just copy this first customer. I need to copy the headers also. Let me try that. There are two rows which I have copied. Let me paste the values of these two rows here. Okay. All the values have not come. Okay. Rather than doing that, let me put it simple way. Balance cap. Bal cap. So this is some particular record. Balance is this much. I'll put it here. Number of credit transaction. For that particular customer, number of credit transaction is 3. I'll put that value. Score. What is the score of that customer? 397. HP holding period imputed. What is the holding period imputed for that customer? 8. 8. Occupation salaried, self-employed, self-employed, non-professional. What is the occupation of this customer? Missing. Yeah, this customer occupation is missing. So this one is missing. So I'll have to put it here. Missing. Okay. Let me change this font has come a small, right? What did we see? Y is equal to alpha plus beta 1, 2, beta 2 plus beta 3 and so forth. So this is my alpha. This is alpha. Now I'm in the scoring. I'm explaining how the scoring is happening. Now beta 1 x1. x1 is this. Beta 1 is this. Yeah. This is x2. This is beta 2. This is x3. This is beta 3. This is x4. This is beta 4. The customer is in none of these categories. It is in missing category. Beta should be 0. Yeah. And now we have to do summation of this. This is y. This is y. I have to get probability. Y is what? Log of p upon 1 minus p is equal to y. And when we solve this equation, what we get? Y is equal to ln p divided by 1 minus p. And when we solve this equation, we get p is equal to exponential y divided by 1 plus exponential y. When you solve this equation, this is what you get. So I want to compute probability. So what I'll do, this is y. So expy is, I'll compute, is equal to expy y. And now I have to compute probability. And the formula is expy upon 1 plus expy is equal to this divided by 1 plus this 0.02. Okay. This entire calculation 0.20231. Let us see whether our calculation has been right. 0.023 is a probability. You get the entire concept? So that equation, this is how you solve that. and you get the probability. So internally, this entire thing that we have done is completely done in the predict function. So I don't have to now bother about doing this manual calculation. Only thing that I have to ensure, the data which I have to score, the data for which I want to estimate the probabilities, that data should have the same column names which I passed during model development. Because if you have said age and age variable is not there, how it is going to compute the probability, right? So this is the scoring element. Clear? I have got the scores, but my objective is not to get scores. My objective is use this scores at the development stage. My objective is not to get the scores. In implementation, my objective is to get these probabilities only. But at development stage, my objective is to use these probabilities and then based on these probabilities find out how good is the model. Yeah. So computing probability, this is the syntax. Yeah. Now we are entering into a concept which is called rank ordering. Let me open a new presentation to explain the concept of rank ordering. First we'll understand the concept and then we'll build a rank order table. Okay. Rank ordering. Rank ordering is the one of the most used model performance measure. I'll repeat, what are we trying to do using a predictive modeling? Using a predictive modeling, we are trying to predict the likelihood of an event occurring. If we are trying to do prediction for marketing, we are trying to predict who is going to respond and who is not going to respond. The entire objective of finding who is not going to respond is to not target them. Because by targeting them, you're spending your energy, right? And if you're spending your time and energy targeting a customer who is not going to respond, you have only that much amount of time. Your entire objective is to target a customer who is going to respond. When it comes to risk, in risk, what are you supposed to, loans basically, when it comes to risk and then specifically banking, you're supposed to give loans. When you give loan, you are taking a risk. The entire objective is not to give loan to customers who are going to default. Again, the probability helps you identify who is going to default and who is not going to default. Customer who has got high probability are more likely to default. Customers who got low probability are less likely to default. So end objective of the model is give probabilities, higher probability to customers who are going to respond and lower probabilities to customers who are not going to respond. How do I ensure the model is doing a good job? To ensure that model is doing a good job, I am now going to do a rank order test. So the entire calculation goes like this. This is how your data looks. You have got predictor variables, you have got target. Using the predictor variables and target, you build the model. Certain predictor variables came significant. Yeah. Once you have this data, what are you doing? Using those predictor variables which came in the model, you are scoring the data and then computing probability. So if my model is good, I would have given a lower probability to customer who are 0 and relatively higher probability to customers who are 1. Mind well, this thing cannot be 100% correct. There will be certain customers who have the same set of characteristics, all characteristics same. Is it possible?
Yes.
All characteristics same, virtually almost same. Possible. And one of them is responding and other is not responding. But if all characteristics is same, my probability for that customer in that case would be same as the previous customer. Agreed? Only thing what we are saying is in that segment of customers having same characteristics, if my probability is 0.51, it says that in that segment 51% of customers are going to respond and 49 not respond. So 49 will have still zeros. That is the entire concept. It will not be by chance. It is, they are having statistically. Okay. So the first step, now to test how good my model is, I require these two columns, which are important, because once I have taken all these variables and computed probability, these variables are of no use, because the entire gist is converted into one number, which is probability. So I have got these two columns which are important. I take it forward. I do a rank ordering. I do a ordering of this data based upon probability column, probability value. So assume I'm doing low probability to high probability ordering of this data set. Okay. So this data which was unsorted now becomes sorted. Only thing, this is the step. Just logically keep thinking. Logically keep thinking as I keep talking. Is it possible to do sorting?
Yes.
Possible. If it is possible, then don't think ahead. Why is he doing sorting? At this point, don't keep thinking ahead of what I'm saying. Otherwise, you will miss the entire crux of what I want to explain in rank ordering. Can I, based upon the sorting, break this entire data into 10 groups? So I'll start with the lowest probability and take 10% of the data set and call all of them as decile 1. Then I'll start from here, take 10% of data and call all of them as 2. Then I'll take all of this data and then start saying 3, 4, 5, 6, 7, 8, 9, 10. Deciling is basically, a decile is 10% of data. Industry standard people, whenever they build a model, they finally see rank ordering based upon deciles. So some people come and say, sir, can we create 20 buckets and each bucket have 5% of the population? Go ahead, do. If you want to do with 20 buckets, someone will come, sir, can I create 100 buckets? Go ahead, do. If you want to create 100 buckets also, do ahead. But industry standard, people after lots of working, they have come and realized, okay, 10 is optimal. Okay. But for the sake of asking a question, if you say 20, 20 can be done, go ahead, do. 100 can be done, go ahead, do. No one stops you. There's something called thumb rules, right? And something the industry practices. Industry practices 10, so I've done that. Clear? Based on probabilities, can I create now 10 buckets? Okay. If I can create 10 buckets, then based upon these deciles, can I start aggregating data? So I can say how many customers are having decile 1, right? And of that ones whom I marked as decile 1, can I aggregate and say how many of them are zeros? Can I aggregate and say how many of them are ones? So at a decile level, I can get how many customers are there, how many of them are actually zeros, how many of them are actually ones. So I do that aggregation. For me, at a decile level, assume this is some hypothetical data that you get. Now each decile has got 1000 customers. Here what it shows is in this decile there are 295 responders. In this decile, there are 176 responders. After aggregation, numbers can come anything. Okay, but I'm just taking a hypothetical data that this is how your numbers look. Now we are going to go into steps where we will now understand how to go ahead and create the entire rank ordering table. Yeah, till here, point is clear. First step, I'll quickly re-summarize. Rank ordering is one of the most used model performance measure. Second, this is how my data looks. Initially, I have got predictor variables and target. Using predictor variables target, I build a model. Once I build a model, I use the model and compute probability. Once I computed probability, the predictor variables are of no importance because the gist is now converted into one index number, which is probability. I take probability and target forward. I can rank or I can do ascending or descending sort of entire data based on probability column, because my objective is to have low probability to non-responders, high probability to responders, and that's what I'm trying to test. So I sort the entire data. Once I sort it, can I convert those into groups, saying anyone who has got score from this to this are grade 1, anyone who got score from this to this are grade 2. It's as good as saying grade. We are using a technical term, decile. Yeah. Once I have done deciling, can I do aggregation? How many customers in grade 1, how many customers in grade 2, how many in grade 10? And can I also say how many of those grade 1s have responded? Yeah. Assume this is the kind of table you get. Yeah. This table, I now take it forward. These are the 3 columns which I got from the previous table. These are the 3 columns which I get from the, I'm labeling them as A, B, and C. If I know there are 1000 customers who are 1000 customers in decile number 10, which is the best decile, high response segment. 295 are responders. How many non-responders are there? So I can compute this. So this is D is equal to B minus C. My objective is response rate. Can I compute response rate of this decile? Response rate of this decile will be 295 divided by 1000. Actually, for each of row I can do it. The formula is value in the column C divided by value in column B. That will be my response rate. So here what I see is at an overall level I have got 10,000 customers, of which 787 are responders. When I build the model, after having built the model and converted probabilities and deciling, I see 295 of these responders are actually sitting here. Yeah. And the response rate here is 29.5. What is the response rate overall? 7.9. Now if I see the second decile, I see this is 17.6. Third decile, 11.5. Fourth decile, 7.5. And gradually it keeps going down. Can I say that it is rank ordering? Customers to whom, based on my prediction, I assigned high probabilities, more of those customers in that segment are responding. Customers to whom I said they are not going to respond and I gave low probabilities, less of them are responding. And because this response rate is ordering from high to low or from low to high, whichever way you see, we call it rank ordering. And this is one of the most important tests for a model which is built using logistic regression for marketing or for risk purpose. The reason is, if I say I get 29.5 here, then I get 17.6, and then here all of a sudden here I get 18%. Assume here in this decile I get 18% response rate. Can I take a call? Where to stop, where not to stop? Because 29, I started with 29, I started with 17, then 11, and then 18. It's like, it's like probably you are descending from a mountain. You're descending from a mountain and then you have to again climb another hill before you can completely descend. Now, if there is a hill coming, small hill coming in midway, and you have to again do ascending and then start with descending, will it be a painful journey? Yeah. So likewise, if you have this, it has to flow naturally. From very high response rate segments, gradually it keep going down. It's basically like a color. From very dark color, you keep going, and using a slider, and then you keep going to lighter color. You don't want a slider saying that dark, it going light, and then all of a sudden you become dark, right? So if this occurs like this 7.5 would have been 18. I would have called it as crack in rank ordering. And it's a very big crack. In that case, the model is not acceptable. Okay. However, if this crack, let me erase all the inks. If this crack is say somewhere, this is 3.5, and say here you get 3.6. After 3 you get 3.6. It's okay. A marginal sometimes plus or minus may happen. Okay, and typically this will happen when you will see that the score distribution, if you actually see the probability distribution given to customers in this and this segment, you will see there is a good amount of probability very close to each other. And that's where these kind of things happen. In that case, you will tolerate and accept it and say, okay, minor crack allowed, not major crack. 3.5, and in the next decile, somewhere around 4th, 5th decile, see again this problem can occur. This problem is occurring because of small numbers. So here 30, 23. Now for example, this 18. This 18. Instead of 18, you get 24. If you get 24 here, just because one case, are you going to, this 2.3 will become 2.4 just because of one case? Is that a big, that is called minor. Okay, because when it comes to smaller numbers, at smaller number, one number going up and down is a chance event. That is possible. But 29, 17, 11 and then 18, that is not a chance event. That is specifically some segment you have not properly got into the model, and because of that segment, this kind of a disturbance is seen, crack is seen. So the response rate element is clear. Okay. Now there are further statistics numbers that we see from this trend, and that's what I'm going to show. Again, I'm saying don't think ahead. For the time being, go with my flow. Can I do cumulative? Basically, if I say I stop at only this decile, assume from a marketing standpoint, I say I'll only stop at this decile. How many customers I will target? 1000. If I say I'm going to stop at this level, how many customers I'm going to target? 2000. If I'm going to stop at this level, I'm going to start from here because I got high response on top. So I'm going to target 3. So this is by my cumulative number of customers whom I would target. If I stop at this level, in this data I can see 787 would have responded. But if I stop at this level, how many would have responded? 295, because I only target them. I would have only able to get 295. Yeah. If I target the top 2 decile, how many I'll get? If I target the top 3. So again, I'm doing cumulative of Likewise, I can do cumulative of non-responders. Yeah. So these three columns are clear. Can I convert this number? If I target only these many, what percentage of the total customers I am targeting?
Only 1 by
10 percentage. So I am only targeting 10 percentage of the customers. If I stop at this level, what percentage of customers I am targeting? 20. So I can do cumulative percentage of customers targeted. Now, if I target only this decile, I get 295 customers who are responding. What percentage of potential customers I am getting? 295 divided by what percentage of potential responders I am getting?
Sir, potential respond is 295 upon 787.
295 upon 787.
Okay.
Because if I target everyone, I'll get 787.
Right.
But if I'm targeting only that much, I'm getting
787.
so 295. Likewise, which means if I target this, I'm getting 37.5 percentage of potential responders captured. If I target the top two, what percentage of responders are capturing? 59.8. If I target all the 10 decile, what percentage of potential responders I will capture? 100 percentage, obviously. So I can do this thing similarly for responders. Similarly, I can create this table for non-responders. Okay. So these three numbers now are important. I'm now taking these three numbers forward. Percentage of customers targeted, what percentage of responders I get if I target, and what percentage of non-responders would be there. Okay. Technically, if I target 10 percentage, for the time being, forget model. For the time being, forget model. There is no model. If I take randomly 10 percentage of customers from this 1000, I take random 1000 customers. How many responders will this 1000 customers have?
So 1000 upon 10,000 into जो probability पहला combination ले जाए permutation करेंगे.
So it would have 1000 divided by 10,000. That is 10 percentage of population is what I am targeting. So from the responders also I'll have 10 percentage coming. So here from this 787 approximately 78, 79, 80, 77, 76. See, random is random. There is a probability element. It will not be exactly 78.7 customers. It can be anything which is 78, 79, 80, 77, 76. Any number. Yeah. So the point is, if I target 10 percentage of the population, what percentage of responders I should have got? Let me take a new color. Let me take a black color. If I target 10 percentage of the population, theoretically I should have 10 percentage of responders being captured. But how many responders are getting captured? 37. And how many non-responders are there? Only 7.7. If I see if this has got 10 percentage of the populations, then 10 percentage of responders should be there. Likewise, 10 percentage of non-responders should be there. Obviously, if the concentration of responders is going up, the proportion of non-responders will be lower. This is theoretical. This dot is theoretical. If I target 20 percentage, I should have 20 percentage of responders and 20 percentage of non-responders. So this line would have been a theoretical line. If I target 30%, 30%, 40%, 40% responders, 40% non-responders. The proportion of that with respect to that base would be same. If I target 50% of population, 50% of responders should be there and 50% of the non-responders should be there, right? So, and I would have got this theoretical, but because of the model, what is happening is in 10%, I'm getting 37% responders here. If I target 2 buckets, I get 60%. If I target 3 buckets, 70. If I target all 10, then obviously 100. Likewise, if I do a plot of non-responders. So here, can you see this is the gap between responders and non-responders? This is the gap between responders and non-responders if you target 20%. Is this gap less than this gap? This line, height of this line, is this height more or this height more? Second height is more. The third is still bigger. Fourth is now reducing. If you target 100%, 100%, the gap becomes 0. If you don't target anyone, gap is 0. So what is happening is, as you're doing cumulative and you're trying to see the difference between cumulative responders and non-responders, you will see that at a certain point this gap becomes maximum, and that is called KS statistics, Kolmogorov-Smirnov statistics. Okay, that is called a KS statistics, Kolmogorov-Smirnov statistics. It is a measure of how good the model is separating the good from the bad. And it is one of the most important statistics. The same thing which I showed here out in the graph behind, I can do this in a tabular format. I'll do a difference between cumulative responder minus cumulative non-responders at each decile level. I do this at each decile level and find out the point where this is maximum, and that number is called KS statistics. Why do you require this KS statistics? Let us understand that. Why do you require this? Assume you're now working in this analytics field for 2, 3, 4 years. You have built a number of models and you become so experienced in the domain and the techniques that you can start saying that, oh, what variables will come in the model, how will the trend look like, how will this rank ordering look like, and so forth. Now you are busy with a client meeting, say somewhere in US, and your team is building models for the client. The team member has created this entire rank ordering because this is one of the most important measure the team has created, and the team starts saying, sir, I've created the model. In the first decile my response rate is 29.5% and we are able to capture 37.5% of the total responders. In the second decile my response rate is 17.6 and we are able to capture 60%, and the team member will keep dictating it. Will you have time to hear this if you are busy with your client? So what are you going to say? Can you tell me 1-point statistics? And that 1-point statistic that you will typically ask is, what is the KS of the model? Because the moment you ask that statistics, if your team member says, okay, it is around some 46, you'll say, okay, it's a good model. Because the moment you know it's a KS of 46, you can start expecting that by third decile, this is also one of the important statistics that we quote, by third decile, what percentage of potential responders you have captured. So if the team member says in third decile I get a KS of 46, 47, you can start saying, okay, by that decile you will have captured 72, 73% of total responders. What it means? What it means from a marketing point of view, it means is if I just target the top 3 deciles, which means I'm going to target only 30% of the total base, which I can actually go and market. By targeting only the top 3 decile, I'll get 72-73% of my potential responders. By not targeting the bottom 70, you're going to lose 27-28% of your responders. But for losing that 27-28, you're saving the cost of 70% of base. Right? So that 1 point statistics quickly help you know how good the model is. And that's the reason why this case statistics is important. Make sense? This entire concept is called rank ordering. Yeah. So now let's move to our code in R. I have got the prediction done. My prediction is in prop column. I have to now do deciling. First step is deciling. So I require decile function. Where is that function? Okay. So this function is already available. So what I'll do is this function, I'm not going into logic. How is this function written? This function is written to split the data into 10 buckets. I compile the function. It's a user defined function. Before you use a user defined function, you have to compile it. Once you have compiled it, you can call it n number of times. So I compile it. So now let's go ahead and create decile. Because my deciling has to be on the probability column. So and we are working with the dev sample. So I'll just put it dev. Okay. So I'm doing the decile. The moment I do decile, let me quickly show the data also. Okay, the data is here. So here you can see that deciles have come. Let me sort it by decile. Can you see this decile one has got probabilities which are low probabilities? Let me scroll down completely. These are higher side probabilities relatively. Okay, so we have done the deciling. Now we have to see how good the model is. So I need to run the rank ordering. This is the entire code of rank ordering. Yeah. So I require a data table and I'll call this as .dev. Okay. So I'm converting this into a data table. Okay. What is the name given? Deciles. Deciles. Yeah. Okay. Now there is some logic which is written here. Again, I'm not going into this entire logic. Yeah. I'll quickly run this entire logic. Let me just scroll it. This logic is basically using min probabilities, max probabilities, getting you count of customers, okay, getting you count of responders, count of non-responders, and summing the probabilities. And this entire aggregation it shows is it is being done by decile, and the data is being finally shown as ordered by decile. So this is the logic of creating the initial records. Let me run that. Okay, it's done. Then I showed you various calculation. Response rate, responders divided by count is response rate. Then cumulative. So this is cumulative responders, this is cumulative non-responders, cumulative relative response, which is responders. So I'm now computing relative percentage. So this is the formula, and cumulative relative non-responders, and then I'm computing the KS, which is the difference between cumulative of responder minus cumulative of non-responders. Actually, I should put here absolute. Okay, done. And let us now view this rank ordering table. So it says decile 10. All customers who had probabilities between 0.1 to 0.62 are put in decile 10. How many customers are there? 1000. Approximately we had 50% of the total base taken as dev sample. So I got 1006. As I said, deciling will be approximately 10%. So you see 10, somewhere it is 1005, 1000, 1006 and so forth. How many responders are there? 206. So what is the response rate? 0.20. What is actual response rate that we are starting off with this modeling? What was our actual response rate? 4.5 something, 4.4, 4.5. So in this decile, I'm getting a 20.4% response rate. 0.24, 0.20 means 20.4, right? So that 4.4, which was random, if I target all the customers, I get 4.4% response rate. But if I go selective and now go with probability, out of every 100, 20 are going to convert. With that approach, out of 100, 4.4, which is approximately 4 or 5 customers is going to respond. Now, if you are a sales guy, I give you a lead, I give you a database and say, go ahead and sell insurance product. You contact 100 household, you go. And out of those 100 household, end of day, you get only 4 customers. Will you be happy? No, you will be very dissatisfied that I have to keep going each and every household, sell insurance, and only 4 customers have finally turned up. But if I, as your manager, polish that data, use my some logic, and then you give you that data and say, now go to these household, and from that household, 100 household you go, 20 are taking your policy. Will you be happy? You will be very happy, because if by selling that insurance you get more commission income, you have spent your day better instead of wasting time behind people who are not going to take. So this entire rank ordering is doing that. Yeah. So here I get that. Then again I've got cumulative response and all those things, and then KS. Can you see this? Let us now see rank ordering, whether it is holding. 0.20, 20.4, 6.9, 4.2, 3.6, 2.6, 2.3, 1.2, 0.6. Here there is a minor crack now. What I said, at lower stages, if there is a crack, I'll ignore it because it's a chance event. So at this level there is a crack, I can go ahead and ignore it. So this becomes my first statistics on model. My rank ordering is holding. What is my case? 38, 44, 44, 44.5, 44.2, 42, 44.5. Okay, so that is becomes my second thing. What did I say? If you can know your case statistics, 44, 42, 43, just by knowing case statistics, you can say what is your likely response rate by the third decile. So here you see the number cumulative relative responders captured around 72. Because the moment you know one statistics, you can experience, based on experience, you can get the second statistic indicative number. So here our case is around 44, 45. Yeah. And I'm getting a third decile, which is 72% capture. Making sense? So from a rank ordering perspective, I can say my model is doing good. I've covered one of the important statistics. Yeah. So, sorry. So we have done rank ordering. This is the entire logic which is given to you. This is in the slide. In the slide also more or less the same thing, numbers will come up. Now, second important statistics is basically, I'll go with the chi-square thing. I have built a model. I now have to find out how good is that model fitting to the data. What does model fitting to data mean? Say, let's try to first understand model fit with respect to a simple, this is my X, this is my Y. And the relationship between X, these dots, these are the dots which are data points. Yeah. Now I have built one model which is like this. Is this a good model? Why? Because this dot is observed. This dot is observed, and for corresponding to this value of X, this is my estimated Y. Do you agree? And the difference between this actual observed and this estimated Y is actually error. This is error. You agree? If my error is high, which means fitness of my model is not good. Agreed? Can I now using some statistics, can I find out how good is the model fitting? And one of the model performance measure by which you can see goodness of fit is chi-square. One of the model performance measure is chi-square. And what is the formula of chi-square? Observed minus expected. Now in this case, expected is your estimated. Observed minus expected the whole squared divided by expected. So here we are going to use a chi-square test to see how good is my model fitting to actual data point. What is a null hypothesis? When you do hypothesis testing, because chi-square test is a hypothesis testing. Agreed? Chi-square test is a hypothesis testing. What is a null hypothesis? No, we are not trying to reject it. We are trying to prove a hypothesis, validate a hypothesis. What is a null hypothesis? Null hypothesis is typically status quo. There is no relationship. There is no association. Y is not impacted by X. Okay. Y is not impacted by X. So now here what we are trying to prove is that y, basically when we are trying to prove that y is not impacted by x at a target variable level, when we use this for occupation, we did that chi-square for occupation and other things, what we are trying to say is there the response rate of y in one category very different from a response rate in another category? If there is a difference in response rate in the two categories, we say y is impacted by the other variable. But in this case, the point that I am trying to prove is y and x are, null hypothesis here is x and y is basically the same, and the alternate hypothesis is x is not fitting the y properly. The null hypothesis here is I have built the model, estimate is close to observed. There is no difference between estimate and observed is the null hypothesis. And alternate hypothesis will be there is a stark difference between estimate and observed. And that's what chi-square test always tries to prove. Chi-square test always tries to prove is null hypothesis in chi-square is always there is no difference between the estimate and observed. This is another way of putting null hypothesis. And the alternate hypothesis is there is a difference between estimate and observed. Okay. So here I'm going to do that. So the way it is done, I've got my deciles. I've got my each decile, how many observations are there, and sum of target is actually the observed in a given decile. How many customers are actually won is actually the observed. In a given decile, how many are zeros, actually zeros, is again an observed phenomena, which is actual ones and actual zeros in a given decile is observed. How do I get estimated or expected? Estimated I'll get based upon probability. The model is going to give. So the estimate is going to come from probability. Now, in a given decile, assume there are 10 customers. Probability of first customer is 0.2. Probability of second customer is 0.2. Probability of third customer is 0.2. Fourth is also 0.2. Fifth is also 0.2. 5 customers have got probabilities 0.2. And remaining 5 has got probability 0.25. There are 10 customers. 5 customers have probability 0.2. Remaining 5 have got 0.25. How many responders do you expect in that out of that 10? How many responders do you expect from that
Sir,
10?
out of in one decile there are 10 persons. 10% में each person का probability is 25%.
5% have got 0.2 probability and 5 have got 0.25.
So मतलब इसका क्या होगा मालूम है sir? With every 5%, with every 4%, there will be 1%. So
What you said is right. When the probability is 0.25, out of every 4, 1 is going to convert. And when the probability is 0.2, out of every 5, 1 is going to convert. What you are simply saying is add the probabilities. Logically add the probabilities. So 0.2, 0.2, 0.2, 0.2, 1. 0.25, 0.25, 0.25, 0.25, 1. And another 0.25. So 2.25 customers are likely to respond. So which it means 2 customers are going to respond. But technically it is 2.25. So if I want to now compute expected, what I can simply do In a given decile, what is my sum of the probability? Because each customer I gave a probability, right? I simply sum the probability, it will give me expected number of responders. 1 minus the probability is the probability of not responding. So I sum that probability, I'll get my data.dev, and I'll do it group by deciles and order by deciles. So this is my, because chi-square I cannot directly compute on a, I cannot directly compute chi-square on a continuous variable. Probabilities are continuous, right? So I have to group and make everything categorical. So I'm doing it based on deciles. So I'll get this numbers. Why it is not shown me output? Library. Okay. So let us see that syntax was giving some error. So what I'm trying to do is I'm converting this mydata.dev. I'm just casting it to a data table, and with that data table I'm running the syntax. Ideally that code should have run with a data frame also. No idea why. Now this is how I get my chi-square table. So what this chi-square table, let us quickly copy this and put it in Excel. Data text to column. Okay. So I have copy pasted this. Sorry. This is my observed table. This is my observed. So here I've got, and this is my expected table. This is expected table. And chi-square formula is observed minus expected the whole square divided by expected. So the way this entire calculation will happen is, I'm just explaining now the details. Okay. Chi-square hypothesis is expected is observed is same as expected. That is a null hypothesis. Now using my model, I have predicted the expected, and I want to prove that my model predicted is close to what is observed at a decile level. At each decile level, I am trying to prove that my model is trying to estimate correctly in that decile how many customers are going to respond. So I want null hypothesis to be validated. In this case, I want null hypothesis to be validated. So for that, my objective is that observed should be close to expected. So observed minus expected the whole square. So the way it would be observed minus expected the whole square divided by expected. This calculation has to happen for each and every cell, and the total chi-square value is equal to sum of all these cells then I have to compute degree of freedom. In this, the degree of freedom is typically computed as m minus 1 into n minus 1. In chi-square, the degree of freedom is computed as m minus 1 number of rows minus 1 multiply n minus 1 number of columns. So how many records are there? 10 rows are there. So 10 minus 1, 9. How many columns are there? 2. I should not be computing this 4 because this is observed table. Based on observed table combination of rows and columns, I am creating the expected. So my degree of freedom is 9, but typically for some reason for this kind of modeling, they have said that the degree of freedom should be taken as 8. Why? I don't know the logic. Now with this degree of freedom and chi-square, I need to go and see the chi-square table and get the p-value. I have to get the p-value. And whatever is the p-value, then we have to interpret. So rather than doing that calculation using a table, I'm now going to show that thing here. There is a HL function, Hosmer-Lemoshoff function. This Hosmer-Lemoshoff function. This function is given to you directly. This function, if you see the observed, it does cross tab C bind hat. It computes the y hat, which is y average, then expected, and then does the chi-square observed minus expected the whole square divided by expected. So entire calculation is there. So I'm not going to bother much about it. Directly take this function, compile it, and let me also show you the source. A function for Hosmer-Lemoshoff test, which is a chi-square test, and this function is directly available. I've taken it. So I compile it. Once I have compiled the function, I have to do this with respect to my development target variable, and I have to do with respect to my development probability column. So I'll pass these two to this. It computes it and gives me the calculation. Chi-square for that it is computing is 16, degree of freedom it is 8, and p-value is 0.039. Okay. If the p-value is coming as 0.039, should I accept the model? If the p-value is coming as 0.039, should I accept the model? What is the objective? Observed is close to expected in this case. Null hypothesis is there is no difference between observed and expected. Alternate is there is a difference between observed and expected. If there is no difference between observed and expected, in that case, for the null hypothesis to be accepted, if the threshold is 0.05, what is the p-value that you are expecting? You are expecting the p-value should come above 0.05. So based upon the chi-square test, the HL Hosmer-Lemoshoff test, for the given p-value, the model is not fitting well. Okay. Based upon the test, the model is not fitting well. What does it mean? It means go back to drawing board. See your variables. Which variable you can tweak further such that the model becomes stable. Yeah, you have to go back to the drawing board, see which variable you have to tweak to make sure that the model becomes stable. Let's take a break. Yeah, and we'll come back after the break. Okay. Before going for the break, I had computed the HL, and my number had come 74.5, but the HL which I got from this Horstman-Lemmershort test, that number actually came as 16, the chi-square number. There was some small error in the code, so I just corrected. I'll just show you where that error was. Yeah, here actually in my code when I executed it, it was count. I should have executed this code with sum. Okay. So with sum, when I generate these numbers, if I run this piece of code and then copy paste this table, which I have already done, I have pasted it here in my Excel at the bottom. What was the error is this number of non-responders was actually coming as number of counts. So if I correct that number, this row, only this, sorry, escape, observed responders and observed non-responders. 1 2 1 2. Yeah. So if I just correct this small thing, wait, I have to take that number from here. Yeah. So I have to take this entire table. Let me copy it again. Sorry. Let me paste it somewhere here. Let me paste it. Data text to columns. Data text to columns delimited. Finish. Okay. These are the number of non-responders and these are the number of responders. So let me take this correct table now up. Home paste values. Now this entire calculation, you see the chi-square is 16. This chi-square is same as what chi-square my HL code had given, 16.19. So that was just a small formula error while aggregating I had. So what the way the chi-square is computed for the model is the deciles that you have. At a decile level, you observe how many responders are there and how many non-responders are there. You compare that with respect to the responders and non-responders which you are predicting based upon your model. And the hypothesis that we are trying to prove is null hypothesis observed and expected are same. They are not different. Alternate is they are different. Okay. Now my p-value came. What was my p-value? 0.03. If alpha threshold is 0.05, what it means is my null hypothesis is rejected and alternate is accepted, which means the predicted is not close to observed. I want predicted to be close to observed. Why is predicted not close to observed? If you recollect, during modeling stages, I had mentioned that modeling has got three elements. One is variable transformation, second is visualization, and third is model development. And we keep circulating between these three things. From visualization you may transform, from model you may have to go back to visualization, and from transformation you may have to come back to model development. Now my chi-square is not holding. What it means? Somewhere my predictions are not close to observed. I have to find out where is my prediction not close to observed. I have to go to visuals because the variables are significant, but it is quite possible the variable is significant, but somewhere you are either overfitting or somewhere you are either underfitting. Let me now show you one of the trend for one of the variables. Okay, let me first erase this and come back to my marker. Let me show you one of the trends. First, let's see the business visualization. This is the business visualization of holding period variable. In holding period, what we did? Imputation. Okay, so imputation, we put the imputed values to the imputed values were put to the segment where the response rate was matching. Now if you see the trend, this is the trend. If I fit a trend between the log odds and the holding period value, this is the trend. This is log odds and this is my holding period. Okay, sorry, this is my holding period. This axis is holding period and this is the log odds. Can you see this? This blue line is basically line of fitment. R square is very good, 0.91, and based on R square we took the call that it's a very good fit. But if you now finally observe this fit, you will see that these 4 data points, the response rate for all of them is same. But based upon the graph, here I am going to overfit the prediction for this segment. Here I am going to slightly overfit. Here I am going to exactly, and for this I am going to underfit. The actual response rate is something, but I am giving it value something else. How can I correct this graph? We can group it. So the way I can correct this graph is if I say my data is not till this point. If I say all observations which are after this point are same. Yeah. My fitment is now more better. 0.91 has now become 0.95. Because after that point, there was no difference in their response rate. After this point 18, everyone is same. Based upon this graph. Yeah. So if I can do that, I can get a better fit. So one of the strategy is not impute. One of the strategy now is capping. So what I'll say, any value which is greater than 18, because the trend shows all of them are same, I'll say any value which is greater than 18 is 18. Now this capping is not done for outlier treatment. This capping is done because if someone's holding period is more than 18, be it 20, be it 28, be it 30, the graph says they have got the same probability of responding. In that case, there is no reason why I should have 20, 21, 22 and unwantedly give them because it's a linear equation, why I should make someone overfit and someone underfit? So the step that we have to do now, again, we have to go back, and this back and forth will keep happening. This back and forth will keep happening. So now what I have to do is I have to go back to my development data. This is where my development syntax is. Okay. So now I'm my data dot dev dot dv holding period is equal to if else my data dot dev dollar holding period imputed greater than equal to 18 else dev dollar holding period imputed. Yeah. So what I'm saying, any value which is greater than 18 has to be called 18, else whatever is the value, it's okay with me. So dv holding period imputed is what we are creating. Now this variable will go off. This variable will get replaced by dv holding period. No, this is validation sample. I have to run the model for development sample. Where is my logic? Yeah, this one. I have to run the model for, so dv underscore HP. Why is that HP not coming here? No, we executed. This is the syntax we executed. My data.dev HP. Okay. What I'll have to do is I will take that syntax up. Shift FN. Okay. I'll take that here. dvhp. Okay. I now run this. Okay. I got a new logistic regression model. Let us quickly see the summary of this. Again, all the iterations that you do, you have to see summary, you have to see variables are stable, not stable, are the variables in line with the trend. Because whenever you change, you have to constantly keep checking it. For now, I'm not going to go more in detail of that. Using that model, I have to recompute the probabilities. So I'll recompute the probabilities. If I've recomputed the probabilities, I have to again create the deciles. I have to again see my deciles, and before going to rank ordering, let me now see the goodness of fit, because goodness of fit is where my problem came. I have predicted the probabilities, I have computed the deciles. Let me go with this, and I hope this time it does. P-value has gone from 0.03 to 0.20. If my alpha threshold is 0.05, will I say this model is now a good? It is good. So null hypothesis is now going to be accepted, that expected is close to observed. There's no difference between observed and expected, which means this model is working fine. Are you getting the challenges which are there in the model development? And why is the visualization now important? Because these kind of breaks, this logical thinking is the chi-square goodness of fit is not proper. Which variable can impact the goodness of fit? Ability to relate the visual with respect to the chi-square value, and then saying this variable may be a problematic variable, and then saying this is the correction that will be required. That is an art. That is an art in model development. Okay, now let us see how this rank ordering performs. So I have to do deciling based upon, no, this one is rank ordering. Yeah, I've changed this data. We have already created deciles, right? Decile column, I have, this was the modeling step. Yeah, decile column I have already created, so I can now run these steps. Let us directly jump to the probability. 0.20, 0.07, 0.04, 0.03, 0.01, 0.026, 0.01, 0.01, 0.01, 0.02. So here onwards there is some crack still there. 0.019, but this is 20 and 27. There is some still crack there. 0.01, 0.011, 0.012, 0.01, 0.010, 0.002. The crack which was at the lower level, that has been resolved. But there has been some crack which has come here. Okay. Again, quite possible that this crack may be because of some other variable. This crack can still be because of some other variable. Okay. So let us see which variable could have caused that crack. I have just opened a graph of score variable. Score again is a variable in my model. If you see this, there is a flat trend, there is a growing trend, there is a flat trend, there is a growing trend. But if I actually build the model, what will happen? The trend would be, because we are trying to build a linear model, so the trend would be straight, which means this 3 should have got the same weightage, same kind of response. But these will be over predicted, this will be under predicted, and now this trend is exactly at that center, and exactly at that center there is a crack now. Earlier there was a crack at the bottom. Holding period variable showed me that there is a trend which is flat at the bottom, and that we corrected. Score variable is showing me the trend, there is a flatness in the middle, and that is now exactly coming middle. I need to now tweak this. Okay. And this is what you have to keep doing when you're doing model development. Identify why is that crack, from where it is coming, which variable could have impacted the crack, what can I do to that variable to ensure that crack is not coming. So one possible way is I take all of them together and give them an average value. Okay. Second is I can take these two together and give them an average value. So there is a concept which is called bucketing, and giving a new value to these variables based upon weight of evidence. I have to find out the weight of evidence of each of these and replace their actual value with respect to the segment level weight of evidence. And when I replace the weight of evidence, both of them will get a same number. Instead of someone having a score of 100 and someone having 200, all of these will get a same value, and all of them will get different gradient value based upon where they are. Okay. And then when I take that weight of evidence variable, this will become straight line kind of a trend. This part of correcting that crack by weight of evidence, I will leave as a homework. Okay. So you have to find out what is weight of evidence. Weight of evidence anyways is used in information value calculation also. Now you have to find out how weight of evidence can be used to replace the values of a continuous variables. Okay, that is your homework. If you replace the values based on weight of evidence, this crack will also go. Okay, so this is, now for the time being, I'll assume this, my rank ordering is okay. I'll assume my chi-square is okay. Okay, so what all statistics that we have understood is basically rank ordering, case statistics. Now the third statistic that we have understood is basically goodness of fit. It is called HL test. HL test makes use of the chi-square. These are the three things that you have understood. Now let us understand another test which is called as Gini Index. These are all various ways to evaluate the model performance. Okay. So now let us see what is Gini Index. Let me first explain the origination of this Gini concept. Gini index, this coefficient initially came into play. There was a guy named Lawrence, and he wanted to find out how is this wealth inequality. Wealth distribution in the world is not equal. There is an inequality of wealth. Is there a way by which I can find out how much of inequality is there? Today, the extent of inequality is that there are some top 50, 60 people, the richest 50, 60 people in the world, they own 50% of the world wealth. That's the kind of inequality. So the way it is measured, so what he proposed is, if I can order the poorest to richest, if I order all the people from their wealth ownership point of view, if I take the poorest people at bottom and richest person at the top, and then start seeing what is their ownership. So what I can do is, if I take bottom 10% of the world population, world people, this axis is percentage population. Okay, what is their wealth ownership likely to be? 0.1%, 0.01%, 0.0001%, insignificant. So theoretically, if it would have been equal distribution, bottom 10%, then in that case there would be no bottom. If it would have been equal, there will be no bottom and no top. So 10% of population should have what percentage of wealth ownership? In equal distribution, 10% of the world wealth. So this is theoretical. So this is my theoretical point. If I take 20% of the population and equal distribution of wealth, 20 will 20. Like this, I can go 100 and 100. So this becomes my theoretical line. Yeah. But we know theoretical is not what is practical. And we know that bottom 10% of them hold insignificant wealth. If I take 20%, still they will also have insignificant. If I take 30, they will have something, 40, 50. This top 1 percentile, actually this graph goes like this. Agree? So if I put this like this is 100. And definitely, so this is 100. This area, I call it A. This area, I call it B. Ratio of A divided by A plus B is called Gini coefficient. Ratio of A divided by A plus B is called Gini coefficient. Now you can clearly see, if this wealth would have been equal distributed, in that case, the yellow color is not visible. Let me take a different color. If this wealth would have been equal distributed, this blue line would have moved towards this red line. If it is equal distribution, this blue line would overlap with red line. What will be the area A in that case? 0. Two lines overlapping, it is no area. Area would be 0, A will be 0. In that case, this 0 divided by 0 plus B will be perfect equality, value is 0. Perfect inequality. If A, assume that one person, the most richest person, has 100% of the wealth, that would be perfect inequality and the value would move towards 1. Right? Because this A would be equal to B. Sorry, that value would be, B would move towards 0 in that case. B would move towards 0 and way A, it would become A equal to A plus 0, 1. So higher the value of Gini means higher inequality. For the time being, can you assume from a scorecard point of view, wealth is equivalent to probability. The probability that we are assigning to customers. Wealth is equivalent to probability. Now, if that is the case, would you like to have high Gini or low Gini? Yeah. High Gini. Why high Gini? No, higher the wealth, higher the Gini. No. Why you want high Gini? No. We want high Gini because our entire modeling objective is to give low probability to customers who are not going to respond and give high probability to customers who are going to respond. So if I am saying I am distributor of wealth, I am distributing more wealth to basically customers who are likely to respond. And that's the objective, no? Give low probability to customers who are less likely to respond, give high probability to customers who are more likely to respond. Which means I would like to have a high Gini. Right? So Gini index, if I typically Gini index would be around 45, 46, 50 in that range if you are building a marketing model. Just like in a case statistics, we got 45. There are some benchmarks. If you get a case statistics of 45, 46, 47, from a marketing standpoint, those are good models. Similarly, if you get a Gini index of 45, 46, 47, those are good models. If you get a case statistics which is 70, 80, in that case, definitely it is a good model, but it is too good, just like information value. If you get an information value which is 0.5 and above, it is too good to be suspicious. Similarly, for any statistics, if the statistics goes very high, immediately you should think it is too good to be real. There is something called optimal. These statistics have to be in optimal. Similarly, if Gini index becomes 1, Your Gini index will become 1 when you have rightly predicted all the ones, and to all the ones you have given a probability which is equal to 1, and all the non-responders you have given exact probability which is 0. In that case your Gini index will go to 1. Is it possible to predict such a high accuracy? If that happens, you should immediately understand that you are doing some big mistake in the entire model development. Okay, so don't be very happy you getting a Gini of 0.8, 0.9. Immediately it should be understanding that something wrong is what we are doing. Yeah, but you got the concept, Genie. So now we have covered rank ordering, we have covered KS. In rank ordering we see the KS statistics, we see rank ordering of response rate by each decile, and we also see what is the third decile capture. Third decile capture should be 72, 74, 75%. These are the three things we see in the rank ordering table. Then we have to see a model HL test, Hoshmer, Lemeshaw test, which is goodness of fit test. We have to see Gini. Yeah. Then there is another concept which is called concordance. There is another concept which is called concordance. Let me explain the concept. Assume there is 10 customers. And this is target. And this is probability which the model is assigned. So this is C1, C2, C3. And these are some probabilities which the model has assigned now. Okay. The first step in concordance is you have to create pairs of target 1 and 0. Pairs between cases 1 and 0. So what are the possible pairs? Possible pairs is like C1 is my 1 and C2 is 0. This is a possible pair. C1 is 1, comma C3. C4 is also 0. C5 is 1, so it is not. C6 is 0. C1, comma C6. C1, comma C8. 7 cannot be possible because both of them are 1. C1 is C9 and C1 C10. These are my possible pairs between C1 with respect to others. Likewise, I will have C5 with others. Likewise, I will have C7 with others, with other zeros. Okay. Now, if I take C1 and C2 pair, what is the probability given to C1? 0.25. And what is the probability given to C2? 0.05. Is the probability of C1 more than C2? Yes. In the model, what is our objective? Give high probability to responder and low probability to non-responder. So in this pair, when I'm talking about C1 and C2, concordance, it is in concordance with what I want. Agreed? So that is 1. Is C2, let me put this numbers very close to it. Likewise, I'll have other pairs. This pair is concordant. Likewise, if I see C1 and C3, it is concordant. C1 and C4, it is concordant. C1 and C6, concordant. C1, C8, concordant. C1, C9, concordant. C1, C10, concordant. Now, similarly, I'll have to see with C5 and C2. C5 and C2 first. C5, C2 is concordant. C5, C3 is concordant. 0.12 and yes. C5 and C4 is concordant. It is not. C5 probability is 0.12 and C4 probability is, so this was concordant, this was concordant, this is actually tie. Both of them I give a same probability, right? So it is a tie. C5 with C6 is concordant. C5 with C7, no, it is a discordant. C5 with C9, C5 is 0.12, C9 is 0.05, it is concordant. And no. So there are two cases of discordant. Okay. Likewise, I have to see C7 with respect to others. C7 with respect to C2. Concordance, concordant, concordant. No, yes, no. C7, that is also C concordant. Then discordant, then concordant. So these are all concordant. 7. This one is discordant, this is concordant, this is concordant. 5, 6. So there has to be 7. Yeah? Am I right? So this is I'm comparing with 0.17. Concordant, 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 3 concordance. This is concordant, 4 concordance. This is discordant, 5, 6, 7. Okay. So I got this. So how many concordants are there? Overall? No, not 7. So these 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 cases are concordant. How many cases of discordant are there? 2, 3. How many cases of tie? 1. So total combination is 21. What proportion of things are correct? 17 divided by? What are wrong? And how much is tie? So I can see that 80% of times, if I use this model, I assign higher probability to customers who are likely to respond vis-a-vis customers who are not likely to respond. This is called concordance. Typically, when we use this kind of models, one way of evaluating is called classification table, classification matrix, or confusion matrix, which is basically a cross step between what is your actual and what is your predicted. But typically in logistic regression, rather than creating a classification table, because classification table is not going to give you a right output many a times. There are some challenges of, and the challenges more comes more from an interpretation standpoint. So a better way of looking at things is concordance. How many times you assign a higher probability to a responder vis-a-vis a non-responder. So this is called concordance. Any value which is greater than 70, 75, 80, around that, if you get a concordance, you are building a good model. Okay. So if you are building a good model, you should have a concordance statistics coming around 75, 80. Yeah. So let us see what is the concordance for our model. So to get the inequality, we already understood the concept of inequality, which is Lorentz. To compute inequality, that is Gini, I have a package called init, and if I just run this statement, oh sorry, this one has to be .dev. I have to compute this on the dev sample. Okay, done. So let me see what is my Gini. Okay, 0.58. Okay, then I have to compute concordance. To compute the concordance, there is a full function which is given to you. You have to first compile it. Okay, so I first compile the function, and then I have to pass the target variable. As you can see that concordance was between target and the probabilities, ones and zeros. So the ones and zeros are all available and the corresponding probabilities are available. So I have to pass this to the function, these two columns, and again it has to be dev sample because I'm building on the development data. So I pass these two. It is going to take some time. Why? There are 10,000 observations. In 10,000 observations, some 400, 450 observations are 1. Rest 9,500 are zeros. So combinations will be that many. So 9,500, 450 are ones, assume. 450 are ones. Yes. So that many combinations of between ones and zeros will be formed. If you now see this output, it formed, yeah, it took some time. It formed how many pairs? 42,39,333 pairs. Of those many pairs, 80% of the pairs, it was concordant. 20% was discordant, 0 was tie. Good. So this is how you measure the model performance. These are the various statistics to be seen. Sorry, not this one. Okay. So with that, we have all the statistics measured. Once you have done all of this, what is the next step? Okay. Once you have built the model, what do? You have built the model on the development sample. This thing, what you did, we started with dev, we continued with dev. In between, I explained how to go ahead and cross-check the validation. Some variables during the development have been changed. So will that ratio variable that we created hold? This entire ratio variables that I created, this one, will that hold? No. Because why? I did holding period, not holding period, which was truncated, capped at 18. So now this entire logic, this entire thing, you have to, let me take it down. Once you have built the model, you have seen the model performance is completely holding on the dev sample. After that, the validation element which I said, the ratios, this step comes now. The validation step comes now. So now what you have to do is val cap, number of credit transactions, core, DVHP, DV occupation. Okay, DVHP, let me see in my validation sample whether this DVHP variable is there, not there. So what I have to do is I have to take that syntax, Control C, F, I have to find where is those syntax. Okay, this was the syntax. Yeah, so here this variable, let me take it down, Fn control end. First I have to create this variable for the validation sample. Yeah, I have to val sample. I created for the val sample. Any syntax issues? No, right? Okay. Val cap is available, number of credit transactions, core is available, DV holding period is created, DV occupation. So let me run this step, Control R. Let me just get my logit summary and summary my logit and summary my logit underscore V. These are the two things which I require. Let me take this. After you have done everything on the dev sample, you have to do this summary. We already saw, but I don't know where I copy pasted things. So, and because we have kept changing it, so I'm now taking it again, Control V, and this copy paste will keep happening when you're developing. You will have many worksheets getting created. These sheets, because you will have keep running these iterations, so you will constantly keep have to do this step. Data, text to column, delimited, or probably I'll take fixed width because that's a better way to get it. Yeah, this fixed width is better way. Yeah. So all these things have now properly come. So this is my dev sample. Let me put dev. I have to get the same thing for summary. I have to run it for val sample also. Okay, I have to take these table, copy, I have to paste it. So I'll paste it somewhere here, so that the data text to column fixed width better, because it gives you better. Now what you have to do is ratio, and when before you do ratio, you have to ensure these things are in line, the variables are in the same line. Otherwise what will happen is you put one thing up and other thing down, and also categorical variables have to be in the same order. So ratio. So what I'm going to do is this. This is the estimate of development. This is the estimate of, let us convert it into, right? So all of them also as commas. This one is, yeah. All these values are close to 1. Yes. Occupation, only the last category is 0.55. What I said, the ratio permissible limit is between 0.5 and 2, because 1 divided by 0.5 is 2 and 1 divided by 2 is 0.5. So the permissible limit is 0.5 and 2. Okay. If that is in that permissible limit the values are, there will be no sign change. If the values exceed it, you will see there will be also sign change. We also saw that we should see sign change. What is sign change? Insert these two, I'll do max and min. Max, min. So if I have to do sign change, this is my first variable, equal to this plus this, one standard error, and this minus this. For across all the variables, I have to see that this is negative, this is negative, this is positive, 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 negative, 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 positive, positive, negative, negative. So if I do one standard error plus or minus, sign change is also not there. So my model from a variable beta perspective, it is holding. What next? Using the regression that I have built on the validation sample, I have to now create rank ordering table. I have to see goodness of fit. I have to see Gini Index for the validation sample model. Are you getting? Those should again hold on the validation sample. You got a validation model? See, development, you are building the model. If during development itself you got some problem, you are solving that problem using the development sample itself. Once you have completely done the work on your development sample, now you are going to the validation sample. First thing, you are checking all these betas are stable. If any of the beta would not have been stable, which I already showed you in the very first step, that a particular variable beta was not stable and sign change was happening, right? And that case, even in the validation sample, the ratio would have been between about 2. If you would have done that with an unstable variable, you would have seen that the variable ratio would have gone about 2. So that you would come to know. Now here, if any one of these variables would have not been in this range of 2 and 0.5, actually 2 is also too extreme. 0.5 is also too extreme. The only reason why I'm tolerating this 0.5 is because it is for a categorical variable. In a categorical variable, out of 3-4 categories, one categorical variable can go in this. So I'm tolerating it. Technically speaking, for continuous variable, I would want the ratio to be as close as 1. Probably I want it between 0.8 and 1.2. I don't want it even to go to 0.5 and okay. If that would be the case for a continuous variable, this is the case. For example, DV holding period, it is 1.363. Can it be further improved? Can something be done? Probably something could be done. Okay, I don't know what. This 0.8, can it be something be done for this variable also? This is 1.25. I know for sure for score I can do something because that flat thing that I showed in the score variable, right? And I can replace that with the weight of evidence. So I know here I can do. Probably if I correct this, what may happen is even holding period may get corrected to some extent. So this back and forth in the entire development stage will keep happening. Now you have built the model on the validation sample, you have tested it. What next? For the validation sample, do the rank ordering. So which model you are going to take for testing the rank ordering of the validation data? Which model you are going to do? Typically what you will do is you will take the development model. The model equation that you got on the development sample, you'll take that equation, now run it on the validation sample. You will take the model. See here, the validation regression I executed only to ensure the betas are stable. Now what I'm going to do is, this is my model. This is my final model. I'm now going to take this model. Where is my validation sample? Where is that predict function? Let me find the predict function. Okay. So this is the equation. This one, control C, Fn control N. Now I have to come here. This is dev sample already done. Now I have to do things on validation. On validation using my logic, which is the development model. But which data I am now going to score? Val. I'm now scoring val data. Probability computed. I have to now do rank ordering. So I have to find out the rank ordering data. So let me find decile. Okay. So this is all visualization. So it has gone up very much. Okay, this is the deciling code. So now I have to run this deciling code on the validation sample, and I have to run the, again you have to check the HL test on the validation sample also. So in HL you have to go and use the HL model. So probably this statement, control Fn control end. I built a model HL. I have to now check how is the goodness of fit for the validation model, because the betas of validation can also be correct. It's a range. So I have to check that. So I'll have to do val. So this is what I'll have to compute, and let me name it as HL goodness of fit validation. Okay. So I have to run this, and now I have to check. This is coming as 0.007. Not good. It is not good. Let me check the rank ordering using the validation model itself. Okay. This is the code. Is that deciling? Yeah. From deciling, I have to take this. Control C, Fn control, and okay. So here, this is the deciling. I have to create the decile in the val sample. Val. Using the validation probabilities. Have I computed the probabilities? Wait, I have now here I computed the probability based upon the MyLogit model, right? Let me compute this probability based upon validation model. MyLogit underscore V. Okay, let us compute the probability based upon that. Okay, now let us see goodness of fit. Okay, the goodness of fit is there. Okay, so let me check the deciling using the mydata.val. Okay, so this one is working. Probabilities. Deciling is what I've done. What is this step? Order data frame I don't want. Then I'm creating this another table, my data dot dev. Instead of dev, I have to say well. Okay. So I'm creating a data table, and then using that data table for rank ordering. So this is the, let me also call this rank ordering rank underscore v. Underscore v underscore v. Yeah, everything changed. So I have done this step. My data table I have created. Now I have done this is the aggregation step which I am doing. So let me run the aggregation step. Aggregation done, and then I'm now computing. Okay, this one is left. I'm now computing response rate. I'm computing cumulative responders, cumulative non-responders, converting cumulative into percentages, and then KS. And let's see the rank ordering table. Is the rank ordering table holding on the 0.19, 0.07, 0.06, 0.035, 0.02, 0.016, 0.01, 0.018, 0.01, 0.006? So even the validation model which I built using the validation equation, goodness of fit is holding. Using the validation equation, rank ordering is holding. So even the validation model is stable. So basically the same betas, same variables which have finally come significant, I tested their betas. Those betas were holding on the validation sample. Those betas are holding on the development sample. In case a particular beta would not have hold when I do a ratio between dev and val, and the ratio comes out to be 2.1, what are we going to go do? After having checked the entire model performance on dev, we come to this, and then validation, that variable, one variable is failing. We are going to go back and tweak that variable. Just for in this case, assume, as I said, I would not have tolerated even 1.5, 1.6 for a continuous variable. Assume for score, because we know that there is a flat trend in between, and for score the ratio comes out to be 2.1, and you know there is a flat trend, which means that variable needs to be tweaked. You will tweak that variable. If you tweak the variable, now why are you tweaking? Because that variable is not holding during the validation. During the entire model development process, the variable was holding using a development sample. But only when you came to the val sample, you realized this variable is not proper and you tweaked it. Which means the final model that you are building is actually a function of dev data and val data. Because if it is not holding validation, you are tweaking, going back to development and then readjusting it. And then coming to the validation. And you keep doing this iteration till the variable betas hold on dev sample and validation. Which means that this equation, this model, if you now apply to data which comes from dev data or val sample, if I now create a new sample, 50% was dev, 30% was val. If I merge these two data and take a random sample out of this and now apply this model on this sample to see the rank ordering test, will their model hold or not? It's going to hold. Because in the entire process, I have been constantly building the model based on this data. So the real proof of whether the model is holding or not holding will be based on holdout data. Because that 20% I have not used so far. I have not subjected to it to regression. On that 20, you are not going to run regression. That 20, what you are going to do is simply score based upon the dev model, and then do a rank ordering. If the rank ordering on that holdout is holding, your model is holding. If you are not going with the rank ordering as a model performance test, if you are going with a Gini index, assume whichever test is your final test. If that test is holding on the holdout, the model is holding. So now the final step will be, I have to take this equation, which means now I have to do, where is my predict code? I have to take this predict code, fn home. Probably I can copy this line. Holdout test for rank ordering. This data is my data dot hold. This model I'll have to use dev. Now dev is the final model. Val is not the final model. Val is just a, because val is built on a smaller data set also, so that cannot be your final model. The objective of val was to test the variable betas are stable or not. Final model will be the model which you build on a larger data set, and in this case it was a dev. Which data we are trying to score? Hold. So I'm computing the probability. Okay. So now here, first step, it's saying that HP variable is not there. Holding period imputed. And that's the one reason why you have to keep doing this. Why you should keep doing this DV. Because if you give the same name, the holdout would not have been imputed and it would have scored it. But now it says that HP is not imputed. So I need to find that HP impute. Control F, DV underscore HP. Okay. So this will have to come. Creating derived variables in holdout. Okay, so I have to do that. Again, we have occupation imputed also, right? So let me first just do HP imputed. Well, sorry, not well. Hold. 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 Yeah. So I have to run this step. Okay. Let me view the data also. Not hold. The objective of viewing is just to ensure the variables, okay, these values are properly created. Okay. Now let me run this. I know occupation imputed is not there, but DV occupation not found. Right? What the point I'm trying to show is the variables which were there as part of the final model. If same name variables are not available, scoring is not going to happen. So I have to find DV occupation code also. Okay, this was the logic. So I have to take this code down. Control. I have to create this variable also. So Control C. Anything else? Right? Yeah. So let me quickly see the data also. So this variable is also created. This variable is also created. Let me see if there is anything. If there is nothing else, all variables it is found. It has been able to compute the probability. After computing the probability, what is the next step? Rank ordering. To do the rank ordering, what do I need? Decile. So I have to copy this piece of code and the rank ordering code. Deciling which data? Hold. So I have to say hold, and here probability from hold has to come. So I compute that. This library is already imported. I don't want it. I'm just hold. Okay. Now, if you see, also if you would have noted, I have to constantly keep copy pasting this code. What you could have done, created this rank ordering as a function. We could have created this rank ordering as a function where we say we pass this data frame as an input. This will be a target column. We'll pass the column name of a target, and we'll pass the probability column names. And automatically in the code, it will then automatically find out the entire logic is written, right? So this is where user defined function, which we learnt in R, comes into play. Okay, for now, let me keep doing this copy paste thing, Control R, and this rank ordering, I'll keep rank underscore V only. I'm not changing it. So let me change, sorry, let me run this. So I've done the rank ordering, and this is the rank ordering table for the holdout sample 0.18, 0.09, 0.03, 0.04, 0.03, 0.02, 0.01, 0.005, 0.012. Here this crack is now understandable, 2.5, because the holdout base is just 20% of the population. Okay, so that is understandable. But this crack, if you now continuously see this crack, 0.03, 0.04, 0.035, in all dev val holdout, continuously I am getting this crack. And this crack is completely because of the score variable, which means my model could have been improved if I would have improved the score variable. Yeah. So if you leave a particular variable knowing well that a variable can lead to a problem, and then you don't treat that variable properly, you don't transform that variable properly, continuously you will get that crack. One way of looking at it is saying that in my top 3 decile this crack is not mattering, but it is actually mattering, because 0.03 and 0.04, this 0.04 if it could have been in 3rd decile and this 0.03 would have been in the 4th decile, my 3rd decile is impacted by this tweak, crack. Yeah, so I should solve that problem. But this is how you test the entire model. Once your rank ordering, and most of the time in marketing cases and risk cases, when you're using a logistic, this becomes your benchmark. Rank ordering, the second element that you're going to see is your 3rd decile capture. See, because of that crack, my 3rd decile capture in holdout is 67, but actually in the 73, 67 and 73, that jump is huge drop. I am saying that by 3rd decile I'll capture 73% of potential prospects, but I am able to capture only 67. It is almost 10% reduction in your statistics. That is not acceptable. And this completely is because of one reason only. One variable in which we have not taken proper care. If I see the KS of this, because the KS here was 45, but now here the KS is dropped down to 42 and 42, and it is coming in second decile. Ideally, a good model should have a high KS in second, but if it is a right KS, then it will come in third or second. But here, if from 0.42, it is immediately 0.39. KS is also gone down. 0.44 is become 0.42. Yeah. So all these things are what has to be constantly taken care as you keep doing the model development steps. Once your holdout is holding and you are satisfied, only then you go for deployment. Any questions? If you believe me, it's not that easy to build model. By now you would have realized that how many times I have gone up and down in my code to run the certain steps, and this iteration has to happen. We are only handling how many? 8 variables. First we have to find out which variables to drop. So let me quickly summarize the entire modeling development thing, what all things it entails. A model development, it entails, I'll not go with the summary thing. First is basically you have to remember why is the log odds, the concept of log odds, and we have explained this log odds concept. Then you have to understand that before you start the model development, first you have to get a handle on your data. How many records are given? What is the response rate? What are the variables? What is the meaning of those variables? What is the interpretation? What is the distribution? Categorical variable, frequency distribution, continuous variable, percentile distribution, right? Is there any variable which requires some treatment? Okay, some clubbing, all those things you have to think. Some basic transformations you may want to do, capping flooring P1, P99, standard. But then you may even have to do capping. Now you, after doing a standard capping of holding period, imputation of holding period, I have to cap it at 18. You saw that? Because after 18 it was flat. So then based upon model statistics, you again have to do capping, right? First you are doing capping based on outliers. So outlier detection, missing value imputation, all these things we do. Then we try to find which variables are important. Information value is the most important thing that I typically use and many people use. Despite information value, sometimes some variable may not show good information value and something, and there may be some different tens. So we may even have to go with visualization. After doing visualization IV, you take the significant variables forward, and based upon visualization you may have to do some variable transformation also, and then you go to the model development. Once you have taken transform variable, you do the model development. For model development, thumb rule is divide the entire data into 3 samples: dev, val, holdout. Dev should be 50%, val should be 30, holdout should be 20. If the data is too big, for example I give you 10 million data, in that case don't go with thumb rule. Then you take 1 lakh data, 100,000 observation and say dev sample, okay. 100,000 observation, well sample, okay. Remaining you say holdout is okay. Because data is so big that you don't want to run your development on 5 million observations. Okay. Thumb rule means in normal scenarios, those have to be followed. Yeah. So dev, val, holdout. Then you start with the regression. And when you do regression, you have to see variables are significant. Typically we accept variables at 0.0001. So basically this significance, triple star. So here it is showing 0.001. Many times we used to build models at 0.0001, 3 zeros and 1. Okay. So you have to see the variables which are at this significance. When the variables are coming significant, you have to see that multicollinearity problem is not there in your data set. You have to multicollinearity can be seen using VIF, and some other way of checking multicollinearity is just to create a correlation matrix also. Okay. Then you have to, once you have built the model and you have removed insignificant variables and you have tweaked, transformed some variables which you are not holding, plus or minus one standard error. When you do plus minus one standard error, some variable may change sign. If you see change sign and specifically categorical variables, then you have to probably see, is the beta of that categorical variable overlapping with another category in the same variable. If that is overlapping, you may think of grouping those two categories. Then computing the probability. Once you have computed probability, then you go with rank ordering, KS. Another important statistics is called AUC. I have not given the AUC statistics here because it's not easy to explain. But again, similar to KS and rank ordering. So AUC, you can just go on internet and find what is AUC. AUC called area under curve. Okay. And there are these functions also. I have not executed this. I can, if I use ROCR package and don't understand this part of syntax, just run it as it is. It will give you KS statistics. Okay. Then you have to see goodness of fit. In goodness of fit, we realized that model was not holding, and we had to again go to dev sample, development, and development. Then we found one of the variable was flat, which was holding period, and then we capped it. Then we again built the model. Model was holding now from a goodness of fit statistics. So goodness of fit statistics is there. Gini index is there. Concordance is there. And not thank you. After concordance, the dev model is built. Then you have to run the steps on validation sample. You build a validation model, see the rank ordering with using the validation model, see the beta ratios, see the third decile capture, KS, all these things. If anything fails, you have to go to dev. Probably what would have happened in our scenario, dev and validation both would have given fourth or fifth decile crack. See, one model giving a crack is a one-off possible, but the other sample is also giving crack, which means there is a trend. The trend we are not capturing. See, when trends are shown, trends are displayed in various ways. Only thing is our ability to capture and visualize why is this trend like this. That is an art. That is completely an art. Once you have built a stable model, finally using the holdout sample, you will score it based on development model. After scoring on the development model, you will see the rank ordering statistics of whichever statistics is your benchmark as a model performance. You will see that model performance, and that statistics should be very close to the development model statistics. A deviation of plus or minus 10% is tolerable. However, even 10 is on the higher side. Your aim should be plus or minus 5%. If you aim 5% plus or minus, you may at times accept 7-8% also. But if you go with plus or minus 10%, you will end up accepting plus or minus 15%. Okay. If your that model performance statistics, which in our case rank ordering, is actually deviating by more than almost 8 or 9%. 72 is going down to 67, which is a good drop. For me, third decile capture going down from 72, 73 to 67 is a good drop. Probably I don't want to tolerate it. So, and I also know the reason. I'll actually go and tweak that variable, improve it. ensure the statistic sign line. Finally, you will go and deploy the model. Make sense? So these are the various steps that you have to do during development model. The homework is already given. The score variable is not holding, right? So you have to now tweak that score variable using weight of evidence concept. So you have to go on internet, find how continuous variables values can be replaced using weight of evidence concept, replace that variable, rebuild the model, then see dev val holdout statistics should hold across, and that will be your final model. Thank you. I hope you enjoyed the logistic regression session and you have understood what are the difficulties and challenges that can be involved in it. But that's how the models are built. Thank you very much. I'll send the latest code. Bye.